Okay, so in this video we're going to be talking about some systems of differential equations. And so this is really where most of real world stuff is happening because normally you don't have just one function of interest. Normally you're interested in how systems interact with each other or populations interact with each other, for example. And so as in just to build something to take a look at, here we'll take a look at a model of how rabbits and foxes might interact. And so we'll have to make some model assumptions first. In the absence of foxes, we'll assume that the rabbit population grows exponentially. And in the absence of foxes, we'll assume that or in the absence of rabbits, we'll assume that the fox population declines. And so that's assuming that the foxes only eat rabbits, right? They're not getting other food sources. And so we're thinking of that as having an exponential decline. Okay, and so so far, then, do you remember how to construct the exponential growth model? For rabbits, that would be x prime equals alpha x, and for foxes, then it would be y prime is minus gamma y. Okay, so those correspond to our what happens to our populations in isolation, but what happens when they start interacting with each other? We're going to assume that the rate of change of the rabbit population is proportional to the number of rabbit-fox interactions. What does that mean? That means if there are no or very few rabbit-fox interactions, the rate of change of the rabbit population downward is a lot smaller than if there was a lot of rabbit-fox interactions. Okay, and similarly, the fox population would grow proportional to that. Okay, so how many rabbit-fox interactions are there? Well, if there's one rabbit there, the rabbit could interact with any of the y of t foxes, right? And so if there are x rabbits, then there's x times y, number of possible one-to-one interactions, right? And so if we see an xy term, the xy term is modeling the number of interactions possible. And so we'll just take a small percentage of that as either our growth rate or our decline rate. And so here's our final model then so far. Very simple. X prime is alpha x minus beta xy. So again, this is our growth term and this is our decline because of interactions. And so by that we can identify that x is the prey in this equation. And then for y, in the absence of x, right, then this declines, and so this is marking off that this y is a predator. Good. And so with alpha, beta, gamma, delta, we can look at different models. And so we can do a little bit of analysis before we go to the graphs. And here's just a quick example. You might notice that this system of differential equations because of the xy term, it's a nonlinear system of differential equations. It's also an autonomous system of differential equations. T is not appearing here explicitly, even though x and y are functions of t. And so this is x prime of t and y prime of t. Okay, and the solution to this system then is a set of parametric equations, right? X of t, y of t, they go together. And so just like last time in chapter 2, if we were given an autonomous differential equation, the first thing we did was look for equilibrium solutions. And so how do you find equilibrium? If you're at equilibrium, you're not changing, and so that means that the derivatives are equal to 0. And so if we set the derivatives equal to 0 and solve for x and y, if we have constant solutions there, then those are the equilibria. Okay, so let's go ahead and do that. If I take 0, I'm going to go ahead and factor as well. And so it's important to take one equation at a time. And so in this case, I'll take the first equation and say this implies that either x is equal to 0 or 2 minus 6/5 y is equal to 0. Okay, and then each of those cases I look to the second case and solve for that. So if x is equal to 0 in the first equation, what does that imply about the second? That means that y must be 0 in the second. Okay, so 0, 0 is a solution together. You can't separate those, right? Okay, and similarly, if 2 minus 6/5 y is equal to 0 in the top equation, what does that mean about the bottom equation? That means that this thing in parentheses must be 0, right? Because y is not 0. Okay, and so therefore, wherever the two parentheses here are equal to 0, that would give us our second solution. So here's the solutions to those. If x is equal to 0 in equation 1, then y equals 0 in equation 2. Similarly, if y is equal to 5/3, that'll take this out in equation 1, then x is 10/9 in equation 2. And so we have two equilibrium solutions then. And so in the xy plane, there are 2 points that never change, right, in time. Good. And using the software from Canvas, you can see the plots. And I've made just a real quick video of using this software in the next video. Did I say that twice? Okay, take a look at it. It's kind of fun to mess around with. Here's what you might see. So graphical analysis of our system. Remember that we have a parametric set of equations, and if we use this as our starting point, 1 and like 1/2 maybe, then the solution curve goes around in time and goes up and down and around, and you see that this forms a closed curve. And a closed curve in the xy plane, you might remember from our parametric equations, corresponds to a system of periodic solutions in the x, like x versus t and y versus t. And so remember, this graph on the left is x versus y, and you're plotting curves in the plane. But you can plot those separately, those x of t function and the y of t function, and you can see that sometimes it's easier to see it in one version or the other. So in this case, the x of t is the rabbit population, y of t is the fox population, and you see what's happening, right? The rabbit population increases to some amount, right? And then as it's increasing, so does the fox population. But there comes a point where there are too many foxes for the number of rabbits, and so the fox population starts to make the rabbit population decline. But we don't see an immediate decline in the fox population. It takes a little bit of a lag there before the fox population also starts to fall. And then when the fox population starts to fall, what's going to happen to the rabbit population? Well, it takes a while to recover, but it starts to recover when the fox population falls to about there, right? And so here's, well, actually about here. The rabbit population starts to recover about here. And so the rabbit population starts to increase as the fox population still decreases until you get to a certain level, and then the fox population starts to recover, and the rabbit population is booming, and then you repeat the process. So it's kind of interesting to see this lag response here in the two populations. Good. And so that is one solution to our population model. And you actually do see something very similar to this in the real world, even though our model, this model is very simple, right? It doesn't take into account, for example, other food sources for both populations. It doesn't take into account birth rates or death rates. It doesn't take into account other food sources for the foxes. And so this is just a very, very simple model. But even using this very simple model, we get to see very realistic behavior. Good. All right. So I just wanted to talk about one exercise in the set of homework that I'm going to be giving you. Here are two systems. You'll notice that it's a little bit different than the one we talked about because there's a logistic growth equation here for the two populations. And so here we have one set of predator prey, and here we have another set of predator prey. By the way, I forgot to correct this. This should be a plus sign here because, as you see, right, this is this should be X should be the predator in this system, and Y or sorry, let me rephrase that. X should be the prey in this system, and Y is the predator, right? Similarly, X is the prey in this equation, and Y is the predator, and so that should be a plus sign here. Okay, so in one of these, the prey is very large and the predator is very small, like elephants and mosquitoes. So we're kind of thinking about scale in these two problems. And so in one of these problems, the scale uh, has one set, and then the other it's not. Can you figure out which one is which? Which one has very large prey? You might pause for a second. And are you ready? The left has small prey and the right has large prey. Okay, so by large prey we mean a single X really affects the Y, right? Versus here, a single X doesn't affect Y very much. Okay, that's why it takes, so it's taking a lot more predators, or prey, sorry, okay, those mixed up, uh, to affect the predator population. So in this case, we have a small prey that's needing a lot of stuff here. And similarly, a single Y value, right, really decreases the prey population. Gotta make sure I'm saying that right. Okay, similarly over here, what's happening? We have a large prey and small predator. Okay, I gotta stop there and we'll continue this. We're going to be looking at some systems that we can actually solve right now. Okay,